Hello learners, welcome back to the Statistics for Managers. Today I will be discussing on non-parametric methods. So the contents that I am going to discuss, like importance of the non-parametric method, differences, we will be going through the chi-square test and also the sign test in this particular video. So coming back to the non-parametric methods. So non-parametric tests basically they do not depend on the form of the underlying population distribution from which the samples were drawn. Here most of the times we call this non-parametric procedure as a distribution free test, which at least should satisfy certain conditions. The conditions are like maybe the procedure may not consider any population parameter such as mu, standard deviation, population, or sometimes the procedure is only applied on categorical data which are non-numerical and frequency counts, maybe more variables we can consider. And sometimes these non-parametric procedures does not depend on the form of the underlying population distribution, especially in the requirement of the normality. So when we look at certain aspects, see when to use the non-parametric methods. Suppose if the population distribution is unknown, so we can go for the non-parametric methods, and suppose if the data, the sample size, if it is less than 30, then we can go for that. And if the data type, if it is the ordinal data type of data that we have, then we can use non-parametric methods. And most of the times when we use non-parametric test for testing the hypothesis. And there is another biggest usage of the non-parametric method is we can compare different groups when the different assumptions for parametric tests like ANOVA are not met. So that we can do with the help of the non-parametric test. So here again we will be using for analyzing the relationship between variables that are not linear. So here example Spearman's rank correlation. Actually it is a parametric test. It is a parameter, but still like how we found the relation between the variable, here also we can use by using the non-parametric methods. Coming to the importance. So important when it comes to the importance, like as we have different types of the data, so for certain particular type of data this non-parametric test will be very useful. And sometimes this particular non-parametric test which will reduce the influence of the extreme values, making results more reliable on the presence of the outliers. So when it comes to the limitations also, see when we can use in particular thing, I can say that most of the times we use a non-parametric test when n is less than or equals to 30, that is sample size is less than or equal to 30. limitations. When it comes to the limitations, see, these are not statistical tests like in the parametric test. If we observe, we have so many statistical tests that we have applied on the data, and we have taken the decision. But here, when it comes to the non-parametric test, we have very less statistical power, and sometimes when we are converting the data from one form to another form, in the process we may lose certain valuable information. So that may be another limitation for non-parametric method. Most of the times results are often expressed in terms of ranks or median, which becomes very difficult for us to interpret the value. So when it becomes very difficult for the interpretation, so on what basis we are taking the decision? We are just proving the hypothetical statements. So let us go through the differences when it comes to the parametric test and the non-parametric test. So assumptions. Here in the parametric test, we are assuming specific population distribution. But in the non-parametric methods, as I told, the procedure itself does not consider the procedure. Non-parametric method or test procedure does not take into the consideration of any population parameter. That's why we call that as a distribution free test. And the type of data, if we observe, most of the time parametric tests where we apply this particular test when large samples are there, especially the data should be in the form of the interval or ratio, the quantitative data. But here in non-parametric tests, where sometimes we will be using nominal data, maybe even qualitative data which can be converted into the numerical, and that we are using based on the non-parametric methods. And parametric test basically depends on means and variances, whereas in the non-parametric methods we are just interpreting. That means the end result, which will be in the form of the median, rank or proportion. So we are taking the decision based on the median, ranks or proportions, whereas in the parametric test we are considering the means and variances. Based on that we are taking the decision. And when it comes to the outliers, sensitive to outliers and extreme values, and non-parametric very less sensitive and to outliers and extreme values. When we use the parametric methods, when n is greater than or equal to 30, we use parametric tests, and non-parametric methods, especially when sample size is less than 30, n is less than or equal to 30, that time we apply this non-parametric test like chi-square. Example, chi-square. When it comes to the efficiency, which is efficiency, I cannot tell which is efficient, which is not. It depends on the type of the study, it depends on the research objective, it depends on the problem statement, sometimes availability of the data, samples what they have collected. So when it comes to the parametric methods, especially why they are more efficient, because we are using the higher statistical powers. That's the reason. But here very less efficient when it comes to parametric method. So if we go for the examples like especially in the parametric test, we use correlation, we use regression, we have ANOVA, we have T test, F test is there, Z test is there. But when it comes non-parametric method, chi-square test, most of the times we use chi-square test, Spearman correlation, Wilkerson test, Mann-Whitney test is there. But from the as it all still the learners, so better we start with the chi-square test in understanding the non-parametric methods. As I told you, interpretation, when it comes to this feature, as I told you, interpretation most of the times in the parametric methods we get based on the variances, but here we will be taking the interpretation based on the medians, ranks, or non-parametric measures. So computational complexity, how complex this parametric tests and how complex is whether when it comes to the calculation of the test, which method is more complex. Here in the parametric methods, the computations may be a bit lengthier, but when we have more and more variables, it becomes easy for us to compute easily, and we can convert that any data into the statistical information, and we can analyze and we can take the decision. But chi-square tests, even sometimes if it is 2 by 3 column, easy to solve, 3 by 3, 4 by 4, but when columns and rows started increasing, it becomes more complex for us, especially when we are considering the rank based test. So in the non-parametric test, the foremost and very important test, that is the chi-square test, which belongs to non-parametric category of methods we use to test the hypothesis. Here the chi-square test statistics is compared with the critical value to know whether the null hypothesis is true or false. But the decision of accepting null hypothesis is based on how close the sample results to the expected values. That's what here we try to examine the association between the categorical variables, whether it matches a population distribution. There are certain assumptions for the chi-square test. See, the data must be in the form of frequencies or counts for categories. Adequate size is required, and especially greater than 5. Even while preparing the contingency table also, in the contingency table, if all the cell values are greater than 5, then we go ahead with the calculation of the chi-square test. Otherwise we cannot take up. So each observation definitely belongs to one particular category, and there should not be any overlap. That also we have to keep in our mind while calculating the chi-square test. So the test square, the chi-square test statistics, which is given as chi-square is equal summation of O minus E whole square by E. So here O is considered as observed frequency and E is considered as an expected frequency. Now we can understand with the help of a problem. So the problem here, what I have taken. So a company is interested in determining whether an association exists between the commuting time of their employees and the level of stress. So two variables are observed in this particular problem. One is commuting time. So he has given the commuting time and stress. So stress, again, how many levels we have? High, moderate, low. So at a level, alpha level, at 1% level of significance, we need to find out whether is there any evidence of a significant relationship between commuting time and stress. So here, why we are calling this as a 3 by 3 table? See here, this is considered as first column, second column, third row, first row, second row and third row, and here columns, 3 columns, 1, 2, 3, 3 columns and 3 rows. So I can say it is 3 by 3. And the degree of freedom would be, because I am considering column minus 1 and row minus 1. So column is 3 and row is 3. So 3 minus 1 it is 2 and 3 minus 1 it is 2. 2 into 2 it is 4. So here contingency table we have to calculate. What is this contingency table? See, you have to calculate the expected frequency. As I told here, for calculating chi-square test, what is required? Observed frequency is required and the expected frequency is required. So how to calculate the expected frequencies? So here row total into column total by the grand total. So row total, that means here if we observe in this problem, here totals, this is the column totals and this is the row totals. So under 20 minutes, high stress, moderate, low stress put together 32, and this 116 is considered as a grand total. Now for each cell, that means this is a cell 1, cell 2, cell 3. So again cell 1, cell 2, cell 3, and you can name. So C1 or C2, C3, C4, like that you can name. So here we need to find out that expected frequency. So how to find the expected? So here I have told you a formula. What is that? Row total into column total by grand total. So row total 32, row total is 32 into 44 divided by 116. Now, so if we observe here, we have here 12.4. Now you can calculate manually if you are having calculators. Row total, take the row total 32, and see, when I am taking this row, I am taking this column, which has to be, because for the stress level high, this cell value I have to find out. So 32 into 44 divided by 116 equals to 12.137 I will get, but I have adjusted to two values and I have taken 12.14. So in the same way, 32 53. Now second column, otherwise we will take, let me finish the first row. Now 32 into multiplied by 19 divided by 116. So you will get 5.24 something. So I have taken the 5.24. In the same way, so 32 into 53 divided by grand total 116, you will get 14.62. So like that, we have to find out all the cell values. So how many cells we have? So 1, 2, 3, 4, 5, 6, 7, 8, 9. Total 9 values you will get, because this is the 3 by 3 table. As it is, the size is, the table size is 3 by 3. If it is 2 by 2, you have 4 cell values that you need to calculate. So here, so I have taken all the contingency table, and overall I have taken the totals will be like this. So observed values, what are the observed values? These are the observed values what we have. So like that, so 9, 5, 18. So I have taken 9, 5, 18. First row, second row 17, 8, 28. Third row 18, 6, 7. Expected, already we have calculated the expected values, that is 12.14, 5.24, 14.62. The same expected values we consider. Now with us we have observed value as well as the expected value. Now the test statistics, if I go through the test statistics, what is that? Chi-square test is equals to summation of O minus E whole square divided by E. So here I am taking observed minus expected and squaring the value. Minus 3.14 is squared and we get 9.86, and squared value is divided by the expected value and you will get 0.81, and this is the total summation of the observed and expected frequencies. Now the critical value of chi-square, you have to look at the chi-square critical value tables at alpha, that level of significance 0.01 and degree of freedom. So 3 minus 1 and 3 row minus 1, column minus 3 by 3. 3 minus 1 into 3 minus 1, that is 2 into 2, 4. So degree of freedom will be 4. And what is the calculated value? This is the calculated value. So what should be the decision criteria? So here in the chi-square test, if chi-square is greater than the critical value, if calculated value is greater than the critical value, we reject the null hypothesis. So here when we look at this particular calculated value, how much we have? 9.82. So actually the chi-square test value 9.836 will get, and I have adjusted the 2.2 decimals. And here chi-square table value 13.30. So it is less than, actually. It is not greater than. If it is greater than, we reject the null hypothesis. As it is less than, so we are accepting the null hypothesis. So we can state that the stress on the job is independent of the commuting time. So this is a chi-square test. This can be done for 2 by 2 table, 3 by 3, 4 by 4, and sometimes if they ask even this particular one, especially when particularly if they ask Directly also you can calculate, uh, particularly if they say test for independence of attributes. So that time you have to prepare mandatorily this contingency table. Otherwise manually, individually you can calculate. Normally also you can calculate, and you can have these expected values. So expected value formula is row total into column total by the grand total, so that you have to remember well, and you can calculate very easy. So we have another topic here, the test of goodness of faith. Whether we use this to test to determine whether observed data conforms to an expected distribution. So sometimes we go for the test of independence, but here instead of that, there is much difference is not there. Much difference is not there. If we observe, even the same formula what we are using for the chi-square test, here also we use the same. So here we have one problem. Let me explain with the problem. So a researcher is rolling a 6-sided dice 60 times and obtains the following outcome. So how many phases will be there? So 6 phases, and for each phase, first phase 8 observed is 8, second phase is observed by 10, like that all outcomes are equally likely. So first what we have to do here, equal probability we have to find out, because here where you will get the difference only in the calculation of the expected frequencies. So expected frequencies can be calculated with the hypothesized distribution EI is equals to n into PI, where n is considered as total sample size and PI considered as the probability of ith category. So that's the reason why, see here how many phases we have, total 6 phases. Definitely you will have one phase, so PI will be, probability will be 1 by 6. So EI is equals to n into PI. So what is n? Total sample size. So here we get 60, because 60 times a researcher rolls a 6-sided die 60 times. So we are considering 60 divided by 6, that is expected definitely will be 10. So EI will be 10. So the test statistics, same, the formula what we have used for the chi-square test, the same formula we apply for the chi-square test here also, that is observed minus expected whole square by E. So here I am showing the calculation here manually. So observed value is 8, and the expected frequency is 10. So 8 minus 10 whole square by expected frequency is 10. So like that for all the observed values we are calculating and simplifying, and we have after simplification we have 2.2 degree of freedom, k minus 1. So actually here we have 6 phases are there, so I am taking k as number of phases minus 1, that will be the 5, and again as it is, if chi-square test is greater than critical value, then reject the null hypothesis, and here we fail to reject the null hypothesis, that means we are accepting the null hypothesis. Another important topic, that is the sign test for the paired data, paired sample sign test, which is based upon the sign of the differences in paired observations, say x, where x is the value of an observation from population 1 and y is the value of an observation from population 2. Now here this is very important, how we can define the null and alternative hypothesis, especially for the sign test. So if it is a two-tailed test, p is equals to 0.50, no difference between two types of the events. So negation of that will be p naught equals to 0.50. So here t will be number of plus signs, because why we are calling this as a sign test, because we will be using two signs, one is the plus and another one is the minus. And here we are applying the Z statistics only. So null hypothesis will be stated as p is equals to 0.50. So Z statistics, x mean minus mu by standard deviation, which can be used as x mean minus np divided by square root of npq, where x is number of possible signs observed. So let us have a small problem here. If we observe this problem, then we can understand. So here how many observations we have? Around 13 observations we have. 13 observations without vitamin C and with vitamin C. See, 7 to 2. So reduce. So I am using minus sign here. 5 1 minus 2 0 minus 3 1. Then with below 3 it is below 3. So minus 8 3 below 8 2 by 2. There is I cannot use addition as well as minus. So because it is 0, I am considering this as 0, 4 3 minus. Now here we have one plus sign, that is 4 which has increased to 5. So increased, plus sign I have used. So minus 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 2 3 plus is there, 10 4 1 is there. Another point here, total how many observations we have? Total 13 observations are there, but as we have for one particular observation we got the sign, we have taken the sign as 0. So we will be considering only 12. So we will be considering the number of observations as 12 only. So as probability we are taking it as 0.50, and sorry, this is not 0.50, actually it should be 0.50. Alternative p which is not equals to 0.5. So I am correcting this one, 0.50. And here number of observations, as here it is 0, there is no sign. So I am considering only 12 observations. So n I am considering as 12 observation. So number of minus signs, 10 minus signs are there. So here if you observe sign test, as it is sign test, so we are giving more importance to the signs. So if we calculate number of minus signs and number of plus signs, so out of 12, 10 are minus and 2 are plus signs. So population mu is equals to n into p. So n is total numbers and p is probability is 0.5, that will be equal to 6. And for standard deviation, n into p into q. So 12 into probability into q, that is the quantity 0.5. So always q 0.5 will be there. So definitely you take that value directly, and square root by finding we get 1.73. Substituting all the values that what we have, and we are by substituting the values we get 2.02. See, by 2.02, where here x is actually 10, number of plus signs is 10. So based on, because we are converting the discrete distribution to the normal distribution by adding 0.5 or sometimes subtracting the 0.5, but here we have subtracted and we are taking 9.5. That's why x mean considered as 9.5, though it's not, we have not taken the 10. As calculated value 2.02, which is greater than the critical value, and hence h naught is rejected, because the decision criteria is same like how we have considered in the chi-square test. The same decision rule will be applied on the sign test also here. So this is all about the chi-square test, sign test, test of goodness of fit, especially in the non-parametric test we have considered. So thank you.